Hey, welcome to MIT Abstracts. Today we meet Ginger Schmidt, an MIT PhD student who's saving lives and using lasers to help tackle heart disease. And by the way, she's a BattleBots world champion. Let's go!
Hi, everyone. My name is Ginger, and thank you for the introduction, Fatima. Today I'm going to be talking about how I do both fighting robots and work to save lives. So the plan for this talk is first, I'll talk about the first part, fighting robots, and I do that through BattleBots. And then for the saving lives part, I'll talk about how I use lasers to work on treating heart disease. And then finally, I'll end with some general advice for you all. So the way I got into robotics in general was actually in high school. And in high school, like many of you all now probably, I didn't have a really good sense of what exactly I wanted to do. I did know, however, that I loved creativity, I loved working in a team, and I loved solving problems and creating something that I could hold in my hands and look at, the product of my work. And so one day, around junior year of high school, I stumbled into robotics. And this here is a picture or a video of a robot that I built my senior year of high school with my whole team here. And I just loved the whole process. The idea of sort of having a problem you want to solve, such as shooting balls into a hoop, having a whole giant team to work with, being on a tight timeline, having all that pressure and all that excitement, and then also having to be creative with your solutions. Engineering doesn't necessarily have to be rigid. I think there's a lot of creativity there as well. And I sort of enjoyed all those aspects a lot. And then after high school, one of my mentors invited me to be on a robotics team that does combat robotics. And some of you may have heard of BattleBots before. If you are a parent in the group or a teacher, you may have heard of the original Comedy Central BattleBots, which was in the 90s, but in the past 5 years, it's been revitalized and is now on Discovery Channel. And so here are some of the greatest hits. It's basically just two big robots fighting each other in a giant safe box that no humans can enter.
Those green piano keys, but look at another shot. Weapons up to full speed. And look at that copperhead! Wow! What did it do to Bloodsport? That's a big shot. And another. Wow. Monsoon still speeding around the battle box. This one.
So while it's great fun to build giant robots and fight them in a big safe box, of course, my favorite part, as it was in high school, is the fact that I get to work with my team and to be with a group of people that I can rely on, that I can solve the toughest problems with, and who I know will be there for me day after day. And so I'm really grateful to my whole robotics team, and this is a really big part of my life. And what's really cool is that a few years ago, I had the amazing opportunity to step up and act as team captain with my friend Alex Grant, who's shown here. And since BattleBots is a TV show, they do actually film interviews. So here you can see these are the pits, sort of like in F1. That's our pit stop. It's where we fix our robots if something goes wrong. And then this here is a camera crew, which is really cool to have the opportunity to do that. And then my friend Alex and I working to sort of answer some interview questions, talk about how we're feeling about the fight and so on. And then amazingly, in our first year in season 7, we actually won the championship. And so here's a clip of the very last part of our finals match where we beat Witch Doctor, another really famous BattleBots team. And I'll just show you all here.
The title fight. Witch Doctor's weapon's still working, but it is awfully.
My robot is the orange one named Tantrum. So if you've watched BattleBots, Tantrum is our robot. It's orange. We also have another one named Blip, which is blue.
Painful to watch the legend continue to spin in circles here. I gotta see some movement here.
Yeah, Tantrum might be lining up a big shot to try to get him out of the battle box. No, they don't need to.
The countdown is on. We're gonna have a new champion, and its name is Tantrum. 2, 1, knockout! Look at the face of Ginger Schmidt and Alex Grant. They are champions of the BattleBots world.
So that was definitely one of the coolest moments of my life ever in those 30 seconds when we won BattleBots. I just love the opportunity to be able to do something I love and to do it on TV and to share it with everybody around the world and show that all types of people from all backgrounds can work on BattleBots and do engineering in general. And so I'm still participating in BattleBots. If you want to watch the show, you can watch it on Max or HBO Max. It used to be part of Discovery Plus, and I highly recommend it. It's lots of fun. But besides this other major part, of course, the reason why these are called MIT abstracts is because I'm also a grad student at MIT. And so here at MIT, I am a PhD candidate in medical engineering and medical physics. And what this means is that in addition to doing engineering, I try to use that to solve problems in medicine to save lives. So I sort of get to have my hand in both. More specifically, I work on the circulatory system, or the heart. The circulatory system delivers oxygen within our blood to the rest of our body. So if you look in your wrist, you can see veins, and that's blood that's in them. And the blood that gets delivered to your muscles and to your different body parts supplies oxygen, which is necessary for us to live and to be healthy. At the center of your circulatory system is your heart. And if you put your hand to your chest, you might also be able to feel your heart pump and beat in your chest. And that's because your heart is basically a giant muscle at the center of your body that makes sure blood can travel to everything else. So it's pumping and pushing that blood and then refilling and pushing it out again. However, sometimes the heart itself has vessels that might get blocked. And if the heart vessels are blocked, then we can't get oxygen to the rest of our body, and our heart will start to get sick, as well as the rest of our muscles. And you can think of it as sort of like the pipes that you have under your sink or in your house that deliver water to all parts of your house. We also need those to be clear so that we can turn on the faucet, turn on the shower, and so on. And so if it happens to get clogged, what we can do, and what I work on, is I build lasers that can image these vessels from the inside. And that's to help doctors clear them up so that we can, again, deliver blood and oxygen to the rest of our body. Once doctors are able to get into the blocked vessel with these imaging systems and with these lasers, what I help them do is then place a stent. And a stent is basically a stiff tube that helps open the vessel back up again. So it props it open, it clears the blockages, and it's a stiff mesh structure. And that way blood can flow again. And once blood can flow, we can get oxygen to our muscles so they can be healthy again. And the laser system itself is in a cart that doctors can use, so they can push it up to a patient and then insert the laser into their body and be able to image inside the vessels. And I want to sort of explain to you guys that these vessels are really, really, really tiny in our heart. They're small. And that's why we use lasers, because lasers are really, really narrow and thin. And you can see compared to a coin just how small the tip of one of these systems is. But to support this laser, we need computers, we need batteries, we need all sorts of devices. We need a big screen so that doctors can see, of course, what the images look like. And that all gets packaged into this cart like this. And it takes a lot of engineering. And from these devices, we can capture images of the inside of a vessel. And here's an example of what it might look like. How do we build these medical devices in my lab? Well, all of us are first and foremost engineers. So we have lab benches where we build optical systems. We have other benches where we do soldering, we do building, we do 3D printing, we do designing. And what I actually spend a majority of my time on is also coding, taking these signals and the data that we get from these imaging systems and transforming them into images like the one you just saw of the inside of a vessel that doctors can then interpret and look at to use to treat patients and inform their decision making. But because I work in medical engineering, I also, to make sure I'm building the right thing, get to learn about science and medicine, which is really cool. So this here is a picture of me in scrubs in a hospital, because when I build these devices, I get to test them on patients and talk to doctors. And I also have to learn about anatomy and parts of the body and how the body works in order to best build a device that can image it for doctors. And so I love what I do because I get to sort of touch on both of these. I don't have to be just an engineer or just a doctor, and I get to work in between them. So to summarize these sort of two big main parts of my life, BattleBots and my research at MIT, I have some advice for you all. The first is try new things, even if they are hard. I never thought that I would be able to be on a BattleBots team that was operating at the highest levels. However, I jumped into it in high school. I didn't have any robotics experience. I felt like I came into the game late, but even then I just jumped right in. Same thing with my research at MIT. Before I came to MIT, I was actually working on underwater robotics. And so I had no experience with lasers or with medical imaging systems. And here I am, and I love my work. And the second, which relates to that, is to not be afraid to fail, because you have a lot of time. I didn't figure out what I wanted to do until I was like 16, 17. And even then, I didn't have a plan more than like 3 years out. And so feel free to try something. And if it doesn't work, you can try 100 other things before you need to figure out what you really want to do. And sort of the inverse of that is know your strengths. Not everybody's going to be good at everything, and that is totally okay. Some of your friends are going to be really good at math, but you might be really good at writing, or you might be really good at sports, or it could be flipped. Everybody has a strength, and that is totally okay. And I think it's important to understand what your strengths are and play to them, and figure out how you can use those to benefit your future. And also ask for help from your friends, family, and teachers. A lot of the opportunities that I've received, such as being able to be on a world championship winning BattleBots team, were because I had mentors that helped me get there, that asked me to join their team, that promoted me to be team captain. And so without them, I wouldn't be where I am. So if you're interested in something, or if you have a question, definitely reach out to your friends, families, and your teachers, who are all there to help you. And then look for connections between everything. I think BattleBots and imaging and medical engineering seem very different, but at the end of the day, they're both sort of solving problems and being creative and coming up with solutions. And I just love every part of that. And for me, that's how they're related. And then finally, the last thing is to just say yes to more opportunities. If your parents want you to try something new, try it once. There's no harm. If you come across an opportunity in school, or a new activity, or a new subject, maybe it doesn't seem too interesting at first, give it a go, because you'll never know what happens once you sort of get into it. And then finally, if you are interested in doing robotics, but you're not in high school yet, these are two sort of organizations that I highly recommend. I did first Lego League when I was young for about a year. And then there's also Vex IQ, and there's also tons out there. Feel free to look around. And yeah, that's all. Thank you so much for listening. And I think now we'll do some questions.
Thank you so much, Ginger, for the really cool presentation, for showing us those wonderful videos of your work. And we already have a lot of questions in the Q&A pod. So the first one we have is from a Nord Anglia student who's wondering, why MIT, and how do you like MIT?
That's a great question. And I think I actually have a really good answer for this. So I'm part of a really unique program called Health Sciences and Technology, and it's actually a collaboration between Harvard and MIT. What that means is I take classes at both Harvard Medical School and MIT's Engineering School. So I'm both an electrical engineering concentration here at MIT, as well as taking medical courses at Harvard. And what that means is I get to take cardiology courses at one of the best medical schools in the world. And then I get to study electrical engineering here at MIT, one of the best engineering schools in the world. And then I get to put them together in my research, which is at Massachusetts General Hospital, again, one of the leading research institutions. So I think the environment here in Boston is just so conducive to biotech innovation that there's no other place that I would want to be.
That's totally wonderful. So it sounds truly like the perfect place for you. So we have a few questions related to your research. So some of the Nord Anglia students are wondering, what happens when these, veins or blood vessels get clogged in the first place? Why is that a bad thing? Why is this a problem we have to solve?
That's a really good question. So in order for our muscles to keep functioning, to keep contracting, and to keep us moving, they need oxygen, because oxygen helps convert what we eat in our food into sort of energy for these muscles. And what happens if the flow of oxygen is blocked, then everything downstream of that blockage will be starved of blood. And we need blood, and we need the oxygen to survive. And what that means is those muscles are going to get really tired, and they're going to be less performative, and they're not going to have as much energy. Sort of like when you run out of gas in a car, you need gas for your car to run, you need battery for your computer to run. And when we run out of these sources of energy, our muscles then are not able to perform anymore. And that can be really bad, because if your muscles are sick for too long, then they may never recover. And so that's why it's really important for doctors to get in as quickly and as efficiently as possible in order to clear these blockages, to restore blood flow so that our muscles can sort of return back to health. And that actually has to be done in a very quick amount of time. Otherwise, you could have damage that could last a long time.
Got it. Okay, that makes sense. So a few Nord Anglia students and I might associate lasers with cutting things or, burning holes through things. Can you talk us through why lasers in this case and how the lasers specifically are helping clear those blood vessels?
Yeah, that makes a lot of sense. That's a great question. So you can sort of think of lasers like a lighthouse or like a radar system, where we're sending out a beam of light. And then what we want to do is image the light that is reflected back. So it's almost like a camera you can think of, but with a camera, what happens is we have rays from the sun and from sort of the environment around us, or sometimes cameras also have flash. And what happens is these beams of light move around and bounce and reflect off of things. And the way they reflect and the wavelength and the color of the light that they reflect, we can then capture. And when we capture them, we can form a picture. So instead of, for instance, with a camera where you have like the sunlight, the flash, and all this, and we can form a whole image, with lasers, you just have one beam. And then that one beam allows us to detect something. And then we move that beam and we can detect a bunch. So basically, it's sort of like a very concentrated camera in a sense, but it uses a laser source. So if you know, like radar, for instance, which is sort of similar, where they send out these giant waves and then they measure the waves that come back. Or with like ultrasound systems, you can send out sound waves, sort of like an echo. And then when you yell into a canyon, you'd say like, hey, and then the canyon will echo back at you and say, hey, 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 hey. And you can actually measure that echo to figure out how deep is the canyon, how large is the canyon. And we can do the same thing with lasers. They're just like really, really tiny waves.
Got it. So the lasers are helping us see things that you and I can't really see with our own eyes because it's so small.
Yes, exactly. Because doctors, of course, can't just look inside your heart and see what's going on. Instead, we need to thread this very tiny fiber inside the heart. And then we use that fiber to image it. And then once we can look at what it looks like, then doctors will know, okay, here's the block. Here's where we need to place the device to open it back up again. And here is, for instance, looking totally fine, no problem. So it's really just an imaging system like a camera.
Got it. So, once you've identified this because of this really cool laser that you're helping build, you mentioned that you put in a stent or a mesh. Could you just walk us through what those two devices do again and how long do they last?
Yeah, that's a great question. So the stent and the drug-eluting stent was actually invented here by a professor at MIT many, many years, decades ago, I think. And it is a really great technology. And the way it works is, let's say you have a tube that is compressed like this, and you really want blood to flow through, but you can see that there's not a lot of space for it. And so stents are sort of these like expanding structures where we can squeeze them down really small to get them to go into the vessels, and so that they fit inside our body. And then once they get to the blocked part, we put them in there and then they expand and they open up that vessel so that the blood can flow again, because maybe there's a blockage, something is stuck there, or the walls have collapsed. And then that way we can restore the flow of oxygen.
So it's kind of like holding the doors open, in a busy hallway or tunnel, you're just
Yeah, exactly. It's sort of like braces for your vessels or a crutch, something that makes it strong again, or like a cast, for instance, when you need to protect and keep something safe.
Got it. So one of the Nord Anglia students is wondering, do you have to wear special glasses or protection when you're working with these lasers? Are they dangerous for us?
So it depends, of course, on the energy of laser that we use. If we use lasers that are of the sort of relatively low energy, that's just like the light that we see every day. I think one of the things I really love about physics and engineering, this is going to be a little abstract, but everything is a wave. And maybe one day, if you go into engineering, you can sort of become one with the wave, in a sense, where sort of sounds are waves, light is a wave, a laser is a wave, the surface of the ocean is a wave. When you take a bath in the bathtub, there are waves. The way that your molecules and your atoms shake around inside a table or inside your body, those are all like waves. And so what's cool with lasers is you can just quantify how much energy a laser has. And if it's a safe amount, you don't have to wear any glasses. But if it's an unsafe amount, you can wear glasses that are specific to the laser that protect you from anything. But once we have the laser within the device, within the cart, it is totally 100% safe, no problem. And in fact, you can't actually see it with your eye because we use a really high energy laser to try to get better images.
Okay, got it. And now we have a question from, I suspect, a future engineer from Colegio Menor in Quito, and they're wondering, that mesh that you insert in the vessel, what material is it made from?
So that's a great question. In order to keep them as strong as possible, they're actually metal. And specifically, I believe a lot of them may be nitinol, which is a type of shape memory alloy, although I'm not certain on that. And in addition to metal, a lot of these stents also have a coat of medicine on them that prevent you from sort of having a secondary event. So the medicine that coats the sort of metal structure is there to sort of help you heal while you're sort of physically also being opened up. There are some other experimental stents that are biodegradable. So you can put the stent in your body, and then within 2 or 3 weeks, it'll sort of dissolve and be absorbed by your body. And therefore, you don't have to necessarily live with it for the rest of your life. However, those also tend to be less effective and are definitely not as common.
Got it. And now we have another question related to the laser and the imaging that you're doing. I can tell this is like a hot topic for the Nord Anglia students. Does the image that gets created, is it in color? Is it in black and white? How do you read it and figure out what's going on from there?
Yeah, that's a great question. The image is in black and white because it is a single value that we get for each pixel. So on your computer, for instance, if you look really, really closely at your pixels, you'll see there's both a red, a green, and a blue, an RGB. You may have heard that term. And if you have a white part of your computer and you bring your eye really, really close like that, you might be able to see how there is red, green, and blue. And we need 3 different channels in order to construct a color image. But with the laser system, we only get 1 channel. And so therefore, it's more of a black and white image.
Got it. And now we have a question from a very creative set of Nord Anglia students. And they're wondering, have you or your peers ever worked on making a really, really tiny robot that you could just put in the blood vessels themselves? Or do you plan to in the future?
So I have not worked on these robots, but I know that there are people that are working on them. And they're really cool. And they actually, in order to travel around the body, use magnets on the outside to move around, I think. That's one of the ways in which they can move around. And these tiny, tiny robots are really cool because then you don't have to have a tether. You could maybe go home, or you could like sleep while the robot is in there doing its thing. However, the trade-off with the small robot is that a lot of the engineering we have right now doesn't fit into that small. So if you remember the big cart that I showed you that gets to push up to the patient side, we need all of the electronics in there just to operate our system. We need the computer, we need the laser source, we need all the batteries. So unfortunately, it's not small enough to fit inside. But if that's something you want to work on, that would be an amazing innovation to turn that whole cart into something this small. So maybe that's something you could work on.
I would totally love to see it. And now we have a question from a Nord Anglia student saying, when did you realize you were interested in biology? Did you always know?
So I actually wasn't interested in biology until almost the end of my undergraduate degree, if you can believe it. So I studied engineering my whole life. I always did robotics. And for my undergrad, I also just did engineering. And I think I mentioned I worked on underwater robots, something totally different. But sort of my junior year of college, when I was 20 years old or so, I looked into the future at the field of robotics. And sort of had a tough conversation with myself in terms of what motivates me, what am I interested in, what do I think is important in this world. And robotics sort of had these three main fields that I saw. The first of which is self-driving cars were really popular. The second is factory automation was really popular for robotics. And then the last thing was actually in medicine. There was a ton of robotics investment and a lot going on there. And for me, I just wanted to work in the field that would have the most impact and to help save lives and make people's lives better. And so for me, medicine was the most direct way to contribute to that. And that got me interested in biology and medicine specifically. So I took a bunch of coursework sort of my junior, senior year, studying the history of medicine. I worked at a surgical robotics company and got more involved. And then I decided to join my current program, Health Sciences and Technology, or HST, here at MIT in order to continue those studies. But my opinion is that if you have a rigorous background in engineering and specifically math and physics, you can study medicine or biology or any other field you really want. There's a lot of relation between those fields. So while I am behind some of my classmates in biology and chemistry, I'm able to pick up at least a lot of the big picture concepts just based on my math and physics background.
Got it. And has there been, a helpful crossover in skills? You already had this robotics interest that you'd been working on. Has that been helpful as you're, sitting at the bench and workstation and building these lasers? Have you been able to cross apply some of those tools and skills you picked up?
That's a great question. I definitely have been able to. One of the things with BattleBots is when your robot breaks, you might only have 24 hours to fix it again and turn it around. And that doesn't give you enough time to order parts from online, get things made overseas and shipped. And so you sort of, all you have are the resources around you, and you have to be really scrappy. And you have to MacGyver a solution. You have to ask for help. You have to go to other teams. You might have to weld crazy things or to drill holes in things and do all sorts of creative stuff just to fix your robot before the next fight because you don't have any other option. And in research, I think there's a similar kind of scenario where you're in a lab, you want to try something, and you maybe don't necessarily have the time or the money to build a whole setup, but you got to figure out, based on the tools and the resources that you have, how can we test this hypothesis? How can we put something together and build a little prototype? And so I definitely feel like in my research, I'm able to use my engineering prototype mindset to solve problems and answer questions.
I think it sounds, really exciting. And it sounds like you have to be really creative and thinking on your feet all the time. Now, you used a really good word in there that I wonder if you can just explain to some of the Nord Anglia students what it means. What does MacGyvering something mean? They might not have heard it just yet.
So that basically means to use sort of silly things that may not be meant for something as a solution anyhow. So for instance, I have some friends on a robotics team who, wanted a tube to fit inside a hole, but that hole was just too big. And so when a hole is too big, you cannot add material to that hole, right? The only thing you can do is cut away more material. So then what do you do in a situation like that? You add what's called a shim, which basically is sort of like a sleeve you can put on the post in order to fit it into the hole. And so, this is like the championship robotics competition, and they're looking for material because they need a sort of sleeve of metal, and they can't find any metal that's the right thickness. But what's really, really thin metal tube that we have all around us? Soda cans. And so they actually put a soda can in their robot to fight and win the championships in a following year or in a previous year. I don't remember, but the point is that's like exactly the spirit of like being really creative and thinking of solutions and thinking, gosh, I need a thin metal tube. Where can I possibly find that? And it's like soda cans. They're all around us.
Oh my gosh, that is brilliant. I love that. One more question from our Nord Anglia student who's thinking about applications. So you walked us through, wanting to make an impact through medicine and cross-applying your interests and skills to these lasers now. But they're wondering, are there applications you can foresee that extend past, cardiology or blood vessels? Are there other places that this kind of science could be really helpful?
Yeah, absolutely. The idea of using a laser to sort of image things is extremely broad. And it can be used for all sorts of things. Even within medicine, it's being used to image your throat and your lungs. It's being used most commonly actually in the doctor's office for eyes. If you've ever gone to the doctor's office and you've gotten your eyeball scanned, you have to sit in there and look at a dot and then it'll go zzz, 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 zzz. There's a chance that that was actually a similar type of system, and that's using lasers to image your eyes, which is a more non-invasive way of getting some of those same pieces of information. And then the other thing is you can use lasers for all sorts of imaging. If you've ever seen self-driving cars that have those things that spin on the top of their roof that are going woo, woo, woo. Those are actually lasers, if you can believe it. They're lasers that are basically they're beyond what we can see. So we can't see them because they're not part of visible light. But what they are is they're actually LiDAR systems. So LiDAR that spins on top of these cars. And what they do is they shoot a short pulse of light out, and then they measure how long it takes for that light to come back. So if the light takes a really, really, really long time, they know that whatever's in front of them is really far away. But if it takes a short time to come back, then the car might have to slow down because that means there's something right in front of it. So those are actually also using lasers for imaging technically.
That is neat. I'm never going to be able to look at those the same way again. My goodness, that is too cool. We have a student who's, thinking about the program you're in now. So zooming out from cardiology and your research, but they're wondering, how difficult is it to, balance two different sets of classes at two different schools and having, two different major interests in life, your research and BattleBots? How do you balance everything?
That's a great question. I think the answer is that you, first of all, don't necessarily have to balance everything. It's important to know what you are really interested in, what you want to focus on, and to be able to say no to other things. So that's the first thing, is I feel like I'm selective in what I do and what I spend my time on so that I can spend it most effectively. The other thing is I rely on my friends and my mentors to guide me in the right direction. If I'm feeling stuck, if I'm not really sure how to handle everything, I'll reach out to my professor and say, hey, I have a lot on my plate right now. Like, what should I prioritize? What can we maybe push off until later? And that's also incredibly helpful. And then finally, the last thing is, I think this is sort of more general advice, and this is just my personal opinion, is to pick one thing to be really, really, really good at. So for me, I really, really like math and physics. And so when I'm struggling with medicine or struggling with my medical coursework, what I can do is rely on sort of my mathematical intuition to help me solve some of those problems. Whereas sort of my friends from the other side, a lot of them are really, really good at biology. And so they can look at these systems and understand them really well from sort of this intuitive big picture understanding. And then perhaps may need help with other stuff. And so we can actually work together. And that's the other way that I would say is, if you have a skill set, if you have something that is unique to yourself, you can also find other people that have different skill sets and then work together to solve problems. So we do projects together, we work on homework together, and we study for exams together. And that also really helps to have a strong community and a network of friends.
That is totally great advice. And speaking of math, and I think perhaps your colleagues are very interested in it as well, we have a Nord Anglia student wondering, is some of the math that's on that board behind you related to some of your research, perhaps?
Oh, it is not. I am actually in the HST lounge right now, and we have a lot of different meeting rooms. And so my guess is that some other MIT students were in here probably yesterday working on their homework together with each other and doing their problems on the whiteboard. But if I had to guess, it looks like probability. So probably either probability class or machine learning or something.
Got it. All right. Yeah, walking around MIT, you can see a lot of math on the whiteboards there for sure. Now turning to BattleBots for a few minutes, we have a ton of questions from really interested Nord Anglia students, and they're wondering, is Tantrum your favorite robot? And if not, which is your favorite, and which one was the hardest to build?
Tantrum is always going to be my favorite robot for my entire life. I'll never have a different answer to that. It's like my baby. I have been with the team for, I think, It's been like 5 or 6 years now. And of course, that's the one that won the world championship. And so yeah, I love it. It's definitely my favorite. And in terms of which was the hardest robot to build, I would say probably also Tantrum was the hardest robot to build. For those of you that are familiar with BattleBots, our team also has a second robot named Blip, which is a flipper. So they flip other robots in the air. But with Tantrum, it was sort of the first robot our team ever built. And there were a lot of things we had no idea how to do 5 years ago. We couldn't build a good drive system. We didn't know a lot of things. We didn't necessarily have our batteries all sorted out. And so it was a giant learning process. I think that speaks to one of my points of advice, which was to try something, even if you don't know how to do it or you're new to it. And it took us, of course, a very long time to pick up those lessons. But once we were able to learn some of the key knowledge pieces that was required for BattleBots, it was easier to build the second robot and then the third one and so on and so forth. So Tantrum being sort of like the first one, it went through a lot of changes. It had a lot of things that needed to be fixed. And it's been like a true embodiment of, I think, our journey as a team.
And when it came to naming your favorite robot, why Tantrum? Where did that come from?
That's a great question. So originally, this is sort of a fun robot trivia. Originally, we were going to have 2 robots, and it was going to be a multi-bot system. And they were going to be sort of like angry bees buzzing around. And they were supposed to be like really cute, like little baby robots. So Tantrum comes from like the idea of like a baby being like, rah, like throwing a little fight and being a very sort of bothersome in the box. And so it was actually going to have a twin called Temper. So it was going to be Temper and Tantrum. But then we ended up only building one robot because we ran out of time. So then that was just Tantrum. And then it's stayed with us ever since. And it's got also fists on the robot. So it's sort of like, throwing a tantrum. And the idea is it's like a very sort of sassy kind of attitude giving robot is the idea.
Okay, so that's some insider trivia knowledge for the Nord Anglia students there. And I did love seeing those sassy fists, you jump right up when you guys won. So that was killer. And we have a Nord Anglia student who's wondering, where is Tantrum now? What's Tantrum up to?
So Tantrum fought in season 8 of BattleBots, which came out this spring. And actually next month, there will be a championships tournament that's also airing on Discovery Channel. So Tantrum will be fighting in that. And then currently we're working on hopefully building a new one, experimenting with some ideas and seeing if we can redesign it to be even better. However, the robot itself lives actually in California, where I'm from and where the rest of my team is. So I'm here in Boston, Massachusetts, and the robot itself is currently slumbering, I guess, taking a nap in California, not up to much, because we're working on a new one.
Got it. And we have a question from Junior, and Junior's wondering, how did you feel when you won BattleBots? Can you walk us through what was going through your mind in that video where you're just, jumping up for joy and hugging your teammates? What were you thinking?
Thank you for the question, Junior. That was really an incredible moment. Actually, I didn't show the whole fight, but if you watch the match, within like 30 seconds into the 3-minute fight, we knew we were going to win because we had broke one of their basically drive systems. So they were sort of hobbling around the box, walking really slowly. And at that point, it was our match to lose. So we had to be really careful and really cautious because we didn't want to make a mistake. And so it was sort of us for about 2 minutes being like, oh my God, don't mess up, don't mess up, don't mess up. Like, we got this, like they're broken, like we're totally functional. We can drive around them. We can hit them really good. We just have to be careful. And so then when we won, we had already sort of like hyped ourselves up because we were like, oh my God, is this really happening? Is this happening? But then we can't cheer yet because the match hasn't ended and you never know what could happen. Our robot could randomly catch on fire due to an electrical problem. The drivetrain could suddenly stop working and then we'll be counted out. So, at that point for like 2 minutes, we were on edge because we were like, oh my God, like, did we win? What's going on? And so by the time it happened, it was like truly incredible. Another thing that was really cool is I was actually the first woman to win BattleBots as well. So I think for me, that was one of the most important and most exciting parts, is being able to represent that and being able to sort of represent all of the women that have been in BattleBots before me and how much work they'd been doing for decades, because I'm actually relatively new to the whole sport. So yeah, honestly, it was one of the best moments of my life, and it's really cool. And I hope we can repeat it again someday.
I hope so too. And I think Nord Anglia students and I both really love that video, and we're going to have to replay it a few times and watch that whole match at the end for sure. So now we're coming up on time. Ginger, I'm not even kidding. We got hundreds of questions remaining in this Q&A from interested Nord Anglia students, but I'm going to leave you with this one. So you've talked us through your really cool research, working on these lasers and finding better ways to image inside blood vessels to help people. And you also walked us through your work in BattleBots. What are you thinking of in the future? Are you going to pursue a particular direction related to either of these two avenues?
So I actually have truly no idea what I want to do in the future. I would say I'm really stuck between two things. I would love to go into the sort of real world and work for a company building medical devices that doctors can sort of use. The thing about doing research here at MIT is a lot of the work we do is very conceptual. It's very sort of based in ideas, and it's not necessarily a finished product that doctors around the world can purchase and use on their patients. So I think it would be great to move into a company where I could work on that and could translate those ideas, especially as someone who is sort of in between both engineering and medicine and having that unique perspective. However, I really love prototyping, ideation, creativity, and solving problems, which is what I sort of do now in my research and with BattleBots. And so that makes me want to stay in research so that I can continue to sort of solve unanswered questions, to work with a team of people. So yeah, I have no idea, but what I can tell you for sure is that I want to work on problems that matter. I want to work on problems that can impact a lot of people and make a difference. And I want to work on problems that are fun for me to do, that make me sort of excited to wake up in the morning, that make me want to tackle them, that I sort of think about nonstop.
Well, that is just totally wonderful, Ginger, and we cannot wait to continue to follow what you do and all the people you help. And now, Nord Anglia community, I just want to cue you in to our upcoming abstracts this fall. We got really exciting things coming your way. We have new plastics for the future next month, growing your home with bacteria after that. And then we have mutations and communications, twin PhDs. So it's going to be totally, totally wonderful. And we are so grateful to Ginger for joining us today and for sharing with us all of her amazing, amazing work. Thank you so much, Ginger.
Yeah, of course. Thank you all so much for having me.
Of course, our pleasure. And I'd like to also thank the students, teachers, and Nord Anglia parents who are on the call today for joining us and for making this abstract so fun and for asking amazing questions. Lastly, I'd like to thank the MIT Nord Anglia Education Collaboration for making this series possible, and we are really excited to see you next time. All right. Bye, everyone. Bye, Ginger.
Bye.